Neural global shutter. We restore distortion-free videos from a rolling shutter camera by connecting its global reset feature and deep learning. Image sensor is an essential component of converting photons into digital signals. It comprises millions of spatially distributed photodiodes, namely pixels, performing photoelectric conversion and charge accumulation when photons arrive. Every pixel acts reset, exposure and readout sequentially. A key design of image sensors is scheduling the exposure time and readout time of different pixels to reuse limited readout circuits. This scheduling function results in two different shutters modes: global shutter, GS, and rolling shutter, RS. GS-based image sensors expose all pixels simultaneously and transfer accumulated charges to a storage area before readout. But the requirement for additional storage increases their cost and leads to more noises. Differently, RS-based image sensors expose pixels scanline by scanline with a time delay. The overlap of exposure and readout time leads to a higher frame rate. Besides, exemption from additional storage area attributes to RS sensors lower cost and fewer noises. Therefore, RS-based image sensors are mostly used. Unfortunately, RS sensors bring distortions when scenes or cameras undergo motion. The faster the movement, the larger the distortion. The RS distortion obstructs vision systems equipped with RS sensors to precision-sensitive applications, such as automatic car. Extensive research has been conducted on correcting RS distortions. They estimate the motion and then warp the distorted pixels. However, most of the existing work relies heavily on the prior assumptions of scenes or motions. Besides, the motion estimation steps are either oversimplified or computationally inefficient. In this paper, we investigate using rolling shutter with a global reset feature, RSGR, to restore clean global shutter, GS, videos. RSGR exposes all pixels at the same time like GS rather than scanline by scanline with a constant time delay like conventional RS. The distortion looks like a special blur mixed with brightness inconsistency. This feature allows us to convert the old RS rectification problem into a deblur-like one. We build our model with the encoder-decoder structure used by most video deblur methods. Our method contains three main components. Firstly, a spatial-aware feature encoder with two special designs: exposure encoding, EE, and spatial attention, SAA. These two components enable the encoder to be adaptive to the exposure duration. Thus, our model can accept inputs with different resolutions and exposure directions. Secondly, the long-term temporal aggregator. It used two recurrent neural networks, RNNs, to propagate long-term information along the time axis bidirectionally. Thirdly, the short-term temporal aggregator that uses a sliding window to fuse neighboring frames. It consists of a module stacked with a few convolutional layers, a deformable convolutional network and a channel attention. We are not aware of any dataset that contains RSGR videos. Therefore, we build an optic system that captures synchronized RSGR and GS videos. The system employs a beam splitter to divide the incoming light into two parts and feeds them into an RSGR and a GS camera. These two cameras are spatially calibrated with a calibration tool and synchronized through a synchronization circuit. Besides, we also ensure the RSGR camera's exposure duration of the first scanline equals the GS camera's exposure duration. Thanks to the optic system, we can train our model in a supervised fashion. Here we show our video results. Our algorithm corrects mixed spatial varying blur and brightness without introducing additional distortions and flickering. Remarkably, thanks to our carefully selected loss function, our rendered videos are noise-free even though there are noises in the supervisory signal. Compared with other algorithms, such as GSD blur and RS rectification, our algorithm achieves the best performance. It consistently outperforms others with a large margin on all evaluation metrics. Our RSGR solution shows its superiority to the RS solution. Especially, it is good at dealing with significant motion indicated by lower neighboring metrics. Our solution goes ahead of the RS solution with a large margin when Xi is small, indicating a large exposure duration. Although our performance decays with the increase of Xi, we are still superior to the RS solution. Except the effectiveness, our solution without explicit motion compensation is also more efficient than existing RS solutions.